and how it started, and most importantly, what are the new concepts which have come in. And it will be a very, very interesting stuff because I'm not going into any kind of details, but you can see that how the neural networks, which are the basis, the basic foundations of learning systems today, they have evolved, and then how these networks can be used for so many very interesting applications. So now how it started is, I mean, we have got learning means learning can be done through either it can be supervised learning or it can be unsupervised learning. Those of you who are attending, you can make a note of it or the video will be given to you. So supervised learning is the learning process which, when a child grows up, then the child, how does he or she learn? He or she learns just by observing the surrounding. The first thing that he or she learns is the face of the mother. So mother is the most important thing. And then gradually, the child, when he or she grows up, when he starts to study, then alphabet studies. So the parents will tell the child that, okay, say this is A, this is B. If you just go back to your days, then you can think about that A, when it is given in a certain, font of A, which is the standard font of A, then the child knows and it extracts a set of features from that character. This is how A is written. Okay, so it will find that, okay, A has got a left slant, a right slant, and a horizontal line in between the two slants. Okay, so it takes a little bit of time for one to really extract the features. Now here in this case, this left slant, right slant, and the horizontal line, they are known as features. Then the child, the parents, they tell the child that, okay, this is B. B has got a vertical line and two loops. So child, while looking at it, using his biological, neural system, not the artificial neural network that we are doing, using his biological own neural system, he extracts certain features and then comes to know that, okay, this is how B looks. Now, this is the learning phase. The first phase is always learning. So then gradually, the child starts learning how the cow looks like, how the dog looks like. Incidentally, this biological system, we extract the features very fast and in a way which is not still very much known. A lot of research is being done at the biological, neural level. There are a lot of papers on neuropsychiatrists, but then the whole thing possibly has not yet been fully understood by human beings. Lots of theories are there. So it is important that we, the human beings, we learn just by observation. And when you are learning, for example, A, the child, the first day, he or she learns A, then the parent will give him that this is what is A, this is also A, another, on handwritten in our childhood, we used to write on the slate. Now, for example, on a paper and pencil, using a paper and pencil, the parent can say that, look, this is what A is. And this is another way of writing A. So the child writes, sees that, okay, this is also A. This is also A. So these are all known as training label. So for training the child, you use some labeled samples. Labeled samples means labeled samples of A. So this is very, very interesting that you need a large number of such labeled training samples to really find how A is constituted or constructed of. Similarly for B, similarly for C, similarly for D. So there are two important things. One is the learnings. The second important phase, only when the child has learned. Child learns from what? From a large number of training samples. In the case of alphabet learning, it is suppose 100 A's you write to the child, and each time you tell him or her that this is A, this is B, 100 B's you give, then this is B, this is C. And the child automatically can extract the features in each of these pattern samples. So we call it as a pattern class. A is one pattern class, B is another pattern class, C is another pattern class. So in English alphabet, we have got 26 classes of patterns. Okay. So far as the English alphabet is concerned. In Bengali, we have 55 different patterns. In Hindi also, in Indian languages, we have got more number of patterns. Chinese, I will not go to that, because later on when you will be studying, you may also study that they have got a peculiar different types of picture type things. So when a Chinese boy or girl, he starts looking at those pictures, then pictures mean a lot of things. Unlike our conventional, Indo-European languages. So number one point then is, this is known as supervised learning. So who is the supervisor? The parent is the supervisor, or the teacher in the class is the supervisor. He or she teaches the child, giving a large number of labeled training samples. Then after the training is over, the child has learned all the features. Then the next level is known as the testing level. Testing level means now some arbitrary character will be given to the child, and the child has to say that whether it is A or B or C or D. This part is known as classification. The child has to classify the unknown pattern, okay, into one of these 26 classes from A to Z. And this whole two processes is known as the, first of all, the first phase is the training phase or the learning phase. After the learning is over, you take the test, give lot of A's, B's, C's randomly. If the child can correctly classify, if you give it say 100 such patterns, it's a mixture, D, C, K, L, T, anything. So child, if it can classify these characters appropriately, properly, then in all the 100 cases, then we say that the classifier is a very good classifier. So child has learned. So this is the whole basis of learning. Now there is another type of learning which is known as unsupervised learning. So in supervised learning, what you need is a large number of training labeled samples. But in unsupervised learning, for example, there is a child who does not have anybody to teach. At IIT, when I used to discuss with my PhD students in some room, then I go to the board and some small set of students, maybe that 5-6 students in the class. And then I used to write something, and it was not the regular class hours, but off class hours. So we had a canteen. So the canteen boy used to take tea for me, bring tea for me. Sometimes the students also used to take the tea. Anyway, now while taking tea, he used to simply stand there. Imagine that boy, a poor boy who has never studied. So he used to look at the board that what is being written. Now to him, it's all Hebrew. He just simply does not know what I am writing. So I asked him one day that why do you wait here for such a long time? Because I mean there are so many other people in the canteen and he has to serve. So he said, sir, I want to learn the characters. What is this, sir? He came to the board. So I said that, okay, so this is very important question. So I said that, look, this is what is A. Whatever the board is full, this is what is A. Somewhere else it is A. Here again it is A. Okay. So I told the child that can you find out all the A's in this whole board? Imagine that instantly he could identify all the A's. Of course, he made a mistake because there were, other similar kind of, mathematical, in the equations, some mathematical symbols. He said this looked like, say, A, etc. But he did it almost completely with almost 95% or 90% accuracy, classification accuracy. This is what the human brain can do. So gradually, I used to tell him that, okay, here is a pattern. You find by matching that where else you can see all these patterns. So he used to really identify. I used to tell my students that, look, this is a very interesting study from psychological point of view, the learning of a human being. So I used to tell them that, okay, tell him that, okay, find out all these patterns which look like D, okay, like this. And he used to find that, okay, here is one D, here is one D, here is one D. Now this is, this is known as he could cluster after doing everything. He could make a cluster that, okay, these A's here, they are similar, so you could cluster them together. They are of the same class. Similarly, B's also look more or less similar. So B's will have another class. C's will have another class. So when a large number of such training samples are given, and there is no teacher. So I told the boy that you go, and then I gave him, because who will teach him? Just nobody in his house who can teach him. So he went to the house, and then one Varna Parichoy, he purchased that. Then I said that every day you find that, okay, this is O. And then where all O is written in this whole book. And wherever you find that O, then you circle it. And he used to come and then show me that whether he has done it correctly or not. So I am giving him of samples, but then they are not labeled. I have not told him that, okay, this is A, this is B, so many B's, because I am not a teacher of him. But he himself, that this is a pattern, the similar patterns he could identify. So similarity identification then is a very important area of machine learning and pattern classification. Now the whole job is, this is known as unsupervised learning, where the boy does not have any teacher. Unsupervised means he has not been supervised by any teacher. He does not have any teacher. It's known as learning without a teacher. Supervised learning is learning with a teacher. That means the teacher teaches in the class. Those who are going to the class schools and all of us, we are fortunate enough that we could get that education at home, maybe at school, etc., at college, at university. But then there are a large number of such students who do not get the opportunity. So this is one way of, using similarity, you can group the patterns, and that is known as unsupervised classification. Is it understandable? So first thing is that there are two types of supervised and unsupervised classification. Next important thing to be understood is, now how do you classify? Now we are not using the human brain. You have to make a machine, a computer, which if you just present A's, then the computer should be able to understand that this is A. You present to the computer 100 such A samples, okay? And then the computer should be able to extract the features of it. So this is again, there are three steps of this. One is the pattern is given to the computer. The computer will extract the features, whether there is a left slant or right slant, or so you have to write a code for that. How do I extract the left slant? From an image, you take an image of a textbook, and then from that image, you find that, okay, which all characters are there. And then how do you find that which all characters are there? You can use, say, for example, all the characters are made up of either a left slant or a right slant or a horizontal line in between, or a loop. For example, B is made up of two loops, is right loop. Sometimes you can have a left loop, like if you invert the B, it will be a left loop. There may be, the slants, right slant, left slant. K means a vertical line, then one right slant, one left slant. There may be complete circle, okay, and then there may be in the loop, there may be different, you can, segments you can think about that this is one feature, this is one feature. You use your own intellect to find how many features are there. English character set is very simple from A to Z. Just today only at home, you find out that if I want to, classify all the A's and B's and Z's correctly, using the simple features like, say, vertical line, horizontal line, slant, left slant, right slant, loop, complete circle, and then U, then inverted U, then V, then inverted V. For example, A, one of the things is two left slants meeting together on top. That is an inverted V. So you try to find out as many such features as possible and write a program to extract those features from each of the characters. Okay, A, B, C, D, from each of the characters, try to extract the features. And then there will not be one A. Take the samples from 10 of your friends, and each friend will write A in his own way, in different ways. So what happens is, now all these 10 or 100 samples that you collect from your 100 friends, all of them write A separately, differently, but all of them are A's. Okay, so what you can do is you can take and you can train the computer, tell them that, look, this is A written by my first friend. This A has been written by my second friend, and let the computer knows that, okay, this is a label training sample, that this is A. So computer only extracts the features from that A. The third friend writes A in another way. The computer extracts the feature, and then computer knows that, okay, how to write A's. So A's can be written in 100 different ways. And all these 100 samples, they form a class of patterns, which is known as A in English alphabet. Okay, so this is a class, pattern class of A. Now, after the computer extracts all the features from each of the pattern, then comes the testing phase. Testing means Now we are taking an exam. Exam is a testing phase. So in the testing phase, in the regular teaching course, you are learning. In exams, you are testing that how the student has learned. So here, how the computer has learned, you give him some unlabeled samples. Give him an arbitrary, say K or S, and tell the computer to classify it. Now the computer will have to classify. Now this classification is the major area of pattern recognition. Feature extraction you can do in your own way, depending on the applications, but classification, there are a large number of classifiers. Some of them are known as, the statistical classifiers. Some classification techniques, they use fuzzy set theory, they are known as fuzzy classifiers. Some again make use of a different kind of approach. Those who are doing computer science and those who have done, say, compiler design and all, the theory of language, from language point of view, we can view a pattern having a structure as from syntactic or from structural pattern recognition. Not many people, they use this technique. This is a computer science student, they can do it very easily. Each pattern class, there may be some, those of you who are from computer science higher standard, maybe third year or fourth year, in your theory of languages, you must have studied them. But then you need not study everything. If you need, say, you can do the classification using statistics. Now, how using statistics you will classify? I'm giving very simple examples. I'm just telling you like a story. So first part will be storytelling. So in this storytelling, in this A, when you have given, then the features have been already extracted by the computer. And after extracting the features, what the computer does, classify, it finds out that, okay, say out of maybe 100 samples which have been given for training, what is the average value of this feature? For example, a left slant. Average, how many number of times it comes. Average, this is known as mean. So in general, any pattern can be considered as, this is a simple example of pattern classification using character, alphabet character recognition. This may be an ECG recognition. The whole world is now based on pattern recognition. There is a pattern everywhere. You talk about, say, ECG machines, what the doctor does. The doctor sees the ECG machine, PQRST, it is coming continuously. And then the doctor immediately can suggest that, okay, this is a normal ECG. With maybe that slight bradycardia or tachycardia, depending on your heartbeat. But then the doctor also can find out just from that ECG pattern that whether there is any arrhythmia, that is whether there is any lack of rhythm in the ECG signal. This is known as arrhythmia. So one may say that this is arithmetic tachycardia. That becomes the classification. So in that case, for example, in case of this ECG signal classification, here also you give to the, what will be the features? Now, what features you will take, that depends on you. You think about that in an ECG signal, there are P waves, there is a QRS complex, there is a T wave, and then there is a blank, and again a PQRST. So this is the pattern of ECG signal, right from the birth, right from the mother's womb to the death. Every human being will be having this ECG. In between, if somebody has got some kind of a problem in the ECG, then that means the rhythm gets disturbed or lost. Then he goes to the doctor. And the doctor now today on seeing, he can suggest that this is a normal ECG or this is an abnormal ECG. Suppose the same thing we want to do using a computer. Say computers can be much better doctors. Why? Because you can train the computer. The computer can learn that what is the normal ECG. What are the features of the normal ECG? Okay. For that, what you need? you need a large number of training data samples. It's very important. Now, unless you have got this large number of training data samples, you cannot do anything. How will you proceed? You cannot proceed anymore. Because with say 5 samples or 8 samples or 10 samples, that okay, these are normal. There are so many variations in the normal itself. A good doctor, an experienced doctor, he can see and he can say that okay, this is normal. Although from the actual prototype mean average normal, it is much deviated. But still the doctor, in fact, yesterday I had a lot of meeting from 10 o'clock to almost 11:30 with Dr. Bhattacharya. So he has one such say pattern recognition problem. So with one ISI student and myself, we joined him. So some interesting problems we were discussing, but how it can be done. Now the major problem in this classification, for example, somebody whether he has got COPD or not, how the doctor, he's a renowned doctor in Calcutta, I think one of the best chest specialists in West Bengal, in Calcutta. So Dr. Bhattacharya, he had, on seeing, he can tell that, okay, this is what. Now, whether we can do it by a machine learning. So machine learning then is a very, very important area. Now, we can do it say, statistically, we can also do it by other means. So in practical systems, there is always, this is what I said is the regular system. But in practical examples, if you just see, then there is always an uncertainty. And Professor Majumdar, while discussing the healthcare system yesterday, he made this observation. I do not know whether you have noted it or not. The major problem in pattern recognition is uncertainty. Uncertainty means it can be in a statistical sense, it can be fuzzy uncertainty, and uncertainty today can be modeled in a very, very, in many different ways. So uncertainty may be that something which was a regular pattern, okay, for example, this is for the load forecasting, load profile in electrical engineering, this is a very important problem. So from the load profile, if you can have a regular pattern, then we know that, okay, it is from the historical data. Every month I get this kind of a bill and I have got this kind of a load profile. But then suddenly, if you start finding that it's aperiodic, sometimes it increases, sometimes it decreases. So it is influenced by some external factors. These days it's so hot. So if you have got an AC, then you may tend to use the AC for a longer duration. Okay, so naturally that is an external factor. The weather, such as weather, event, some event has happened and a lot of lights, a lot of fans, a lot of TVs you are using. So a lot of people have come to your house. So naturally it is an uncertainty and it's an aperiodic part. For example, the customer behavior, this is an aperiodic part. During Chaitra sale, a lot of ladies, they go to the market for purchasing the stuff. Now that is because of Chaitra sale. Now this is the customer behavior during certain times of the year. But then this then becomes, there's an uncertainty. More importantly, there is a noise part, which, as you know, most of you may be from electrical or mechanical sciences group, electronics, computer science, IT. Remember that in engineering does not mean that you will always get the appropriate, the regular behavior and you will be able to predict. It is the noise part of it which is more important. In electrical sciences, we call it as the uncertainty due to the noise which is added with the signal. Anyway, I'm not going into it. The whole history, now when people started doing the learning, the machine learning, supervised learning, unsupervised learning, then at the same time, there were researchers. I mean, the first man to talk about it is known as, McCulloch and Pitts. In 1942, when the Second World War was going on, and imagine that even those days, this great, one of them was a mathematician, the other one was an electrical engineer. So they gave the formal definition and a model of a neuron, how the human neuron can be modeled mathematically. So that was a revolutionary concept, and that was possibly, they suggested that the very primitive model today. But then that's how it started in 1942, McCulloch and Pitts. And from that time, there have been a lot of different, stages through which the evolution, everything evolves. No concept comes just overnight. Everything has got a historic evolution. So as it just progressed, then it was found that, okay, there were some efforts which were not very, successful. Like one of them is the concept of perceptron. There was a scientist from MIT, his name was Rosenblatt. So Rosenblatt, he said in late 50s that, okay, I have developed a machine which can classify the patterns. Okay, so all the industries came to him and they said he started doing some patents, industries came to him and industry said that, okay, what is, you do this pattern classification. So 2 class, 3 class problem. So they started giving it. So, but then very soon it was found that the Rosenblatt's perceptron was not the correct answer to pattern classification, because it can classify only those patterns which are, linearly separable. So this is very interesting.
Sir, I'm sorry to interrupt you. Okay, sir, that McAfee was there in the screen. Okay. Some antivirus something was in the screen, sir. That's why.
Yeah. Suddenly it came. Yeah.
Okay. Thank you, sir.
Now suppose there are 2 classes. One is class 1, one is class 2. Class 2 I have written as class -1. Okay, so the basic idea about pattern classification is, what does it mean that patterns in class 1? So there are 2 features. One is x-axis, is F1. One is y-axis, that is F2. Suppose you want to classify the patterns of the leaves of a tree. The leaf of a tree, it may be an elliptic mostly, isn't it? So you can take the major axis as x-axis here and minor axis as y-axis. You can take, mango tree and you can take bale tree. So I have to classify, I have to train the computer using lot of mango trees, and then you can give them lot of bale trees. This bale is another tree you can think about. Now the leaves of these patterns, they will be divided into 2 classes. The class 1 may be, say, mango trees, where the x and y axis are much more. That is, both the major axis, because mango trees are much bigger. Major axis and minor axis, for example, they are bigger than the y class, which is, major axis and minor axis is much smaller. So what does pattern recognition or learning means? After you learn, you have to find the equation of a line. You can see that straight line which demarcates between 2 pattern classes. One is class 1, one is class 2. As you can see that here we have shown that one red line which demarcates between 2 pattern classes. Now this is called a linear classifier. What will happen? What will be the equation of this line? If you say x1 is one of these features, x2 as another feature, then the equation of this line will be, say, w1x1 plus w2x2. What are these w1 and w2 and all? So basically, they gave the initial concept of the neural network was that, okay, you feed the 2 things, the x1 and x2, to one of the neurons. So this is the model of a neuron. What does the neuron do? The neuron will first adapt the X1 feature and X2 feature, but it will not be simple addition. It is a weighted addition. That means X1 is multiplied with W1, X2 is multiplied with W2. W1 and W2, they are the two weights. And finally, you get a sum. It is a sum of the weighted sum of two inputs. And then sigma we have written, this is a summation symbol. So after summing up, then in human neuron also, this is a neuron model. We have got a nonlinearity. What kind of a nonlinearity it is? It can be, you can take different types of nonlinear functions. So it is important to find here that this kind of, it is a threshold function, very simple nonlinearity. X-axis and y-axis, the second part is a nonlinear function part. So it goes through a nonlinear function part, and then if the output is obtained. So for all the patterns in class A, they will have one output, type of output. All the patterns in class 2, if you take that W1, X1, and initially you can have W1 and W2 as randomly, then gradually as the pattern recognition progresses, then if it's a, the computer makes a mistake, then the error is back propagated and then it is corrected. Finally, I will come to the next one. Time is less. So this is an activation function. You will be studying all these things when you will be studying a neural network in much more detail. But traditional neural network is like this, that it has got a three-layered network, input layer, hidden layer. And the input layer, there you are giving the features. What are the features? For example, as I said, in case of ECG classification, there is a P wave, the amplitude of P wave. There is a QRS complex, that is one R wave, so amplitude of R wave. Then there is a T wave, the amplitude of T wave. Then the duration of P wave, duration of QRS complex, duration of T wave. All together, suppose it's a very simplified thing. What I'm saying is absolutely simplified, not that your situation, in real life situation, you have to take much more complex features. But I'm just explaining. So if there are suppose 6 such features, then how many neurons you will keep in this multi-layered perceptron? Because original perceptron I had shown earlier, which Rosenblatt had proposed. But then it was found that Rosenblatt's perceptron is not able to classify the non-linearly separable patterns. In fact, yesterday when I was talking to Dr. Bhattacharya, some ISI, research scholars, they were working on this, and then they did not take care of, the non-linearity of the, so they said, sir, it's not coming, because the two different diseases cannot be distinguished from this data. So I gave them, a lot of time, more than 1.5 hours we discussed. And then they are now writing the codes for that. So it's interesting that you have to think about that if suppose two pattern classes are non-linearly separable, then what will happen? So non-linearly separable means, suppose here, the two classes I have seen that by a straight line you can separate the two pattern classes, the normal ECG and abnormal ECG. Mango tree and Dale tree, you can separate simply by a line. And the line, as you can see, that if you simply rotate the line a little bit, that also will do. That also will be a classifier. Classification means what? Learning means what? Finding these parameters W1, W2, and theta. That's all, nothing more than that. It's very simple. How you find out this weight vectors, X1 and X2. So given any arbitrary sample, for example, Then if it is on the right side of that red line, it belongs to class 1, mango tree class. Left side means it belongs to bell tree class. Is it clear? Then there are patterns. As I said, the things are not as simple as they look like. The patterns, patterns will always be mixed up. So it's known as mixed density functions. That means statistically, when you think about it, you have to do it the statistical pattern classification, where you need a little bit of statistics. For example, the Gaussian distribution function. Yesterday, Professor Mojumdar was talking about the Bayes decision theory. Many of you must have studied it, but then there is a Bayes classifier. So Bayes also had a classifier. So we'll talk about it much more in detail because everything takes time. When, say, somebody studies, then these classes can be taken. This is just an introductory. But nonlinearity means, for example, if they are mixed up, if you do not find any line, straight line, demarcating the two pattern classes. For example, you may find that some of the yellow ones can come in the red zone, in the left zone. Some of the red ones can come in the yellow zone. Then how will you classify them properly? There are many cases where you cannot find a line. The patterns are so distributed that you cannot find a straight line to divide them. Then in that case, if a straight line cannot divide, then there must be a curved line. So you have to find out the equation of that curved line. So it becomes a nonlinear classifier. So Rosenblatt, whatever he did, it could not classify those nonlinearly separable patterns. And that's how this whole lot of neural network research, one of the reasons that it got stopped. Till almost early 1980s, when one gentleman, his name is, he came up with a very important book known as PDP, this Parallel and Distributed Processing, Rumelhart. This group, they came up with an idea and they said that you using only two-layered neural network, you cannot do any pattern classification. This is a two-layered neural network. Like when you have got only one layer or where the input is given, and output layer, YJ, where the output is given. Okay. So using this kind of neural network, you cannot do much. So you have to have one middle layer or hidden layer. You have to introduce it so that you can truly, classify all the patterns correctly. So this is a traditional neural network. But then gradually it was found that, okay, traditional neural networks also were not being able to classify a lot of different pattern classes. A lot of people came up with the different versions of the neural network. Some people, one gentleman, Kohonen, he gave a model of a neural network which could do the clustering, that is unsupervised classification. And then, there was the art network, n number of networks. This is known as error backpropagation. There was error counter propagation. So lots of such neural network models were given. Okay. But then gradually it was found that using even these three layers will not do. You have to make use of more number of intermediate layers. Output layer is always just gives the number of classes. If there are 3 classes of patterns, how many output neurons will be there? 3. If there are 20 features, how many input feature vector will be there? That means 20 neurons will be there. In between, you can put one hidden layer, you can put 2 hidden layers, you can put many hidden layers. So this is known as multi-layered perceptron. But gradually it was found that a new kind of techniques which is known as convolution neural network, which was developed. And I'm not going into the details of this because time is almost, next speaker is there, I'm taking more time. Now this is known as, deep learning, where you can, learn, suppose there are 0 to 9, these outputs. and then 3 is a character. So this neural network should be able to tell that, okay, this is 3. 3 has not been shown. So this should be the highest. This neuron output should be highest. 0, 1 up to 9 will be much less than that. Okay. So similarly, these are the different applications of deep learning. This is how the cars can be recognized. This is how the human face can be recognized. These are all different applications of deep learning. How you can find out the some intermediate features. One of the major problems as I started with was that you have to extract the features. Then the researchers, they said that why the feature extraction is needed. If you take one type of feature, you may get one type of result. If your friend takes another set of features, they can get another set of classification. But why not? You make a neural network which can extract the features themselves. So it has got two purposes. One is feature extraction, and then it can classify. And more lately, there is another very interesting neural network has come up, that is generative adversarial network. I will not go at all into the details, but then the whole issue is, for example, now today you have seen that there are a lot of digital, pictures, portraits which are coming up. And then there are fake images, there are real images. How do you distinguish the two? So this is a model by which, using a random noise and a generator network, one can generate a fake image. And then you can give the real true image. There is a discriminator network. Its purpose is to discriminate between the real and the fake. Okay, so this is a fake image from the generator, left side. You can see that one is a car, another one is also a car, this one is also a car. But then this is the real image. You can see that from the training set, the same 3 cars are there. Fake images have been generated by the generator. Okay, and it has been not so easy. I mean, not so equal. It's still distinguishable. You can distinguish that this is not the exact real image. So discriminator network then should be able to tell that, okay, this is a fake image, this is another fake image, this is another fake image. When the real images are given, they should be able to discriminate that these are all real images. How this training the GAN is done is all a very interesting thing. But then the generator, it can generate a lot of images. And that's why these are, the generated samples. Can you see that just for some arbitrary random numbers, using this network, one could generate 9028, which looks like absolutely, very near to the exact 9028, how we write. The rightmost column, it shows the nearest neighbor from the training set. As you can see that, okay, these are the generations. So generation, one column, one after another, you are generating. The same face is getting generated. So every cycle, after refining the generator is generating. So finally, these are all, the rightmost column is also fake, but then they are looking exactly like the original one. What's the point? So this is, the generated images. There is a deep convolution GAN, and there are people with specs and people without specs. How will you, men and women, how will you, differentiate, distinguish between the two? There is a creative adversarial network. That means this can generate, paints. As you can see that there are the generated images using creative adversarial networks. There's nothing. From nothing you can generate this kind of things. Of course, you need a real sample of this picture, each of these 3 pictures or maybe 6 pictures. From there, you can gradually generate more or less similar to them. Text to image is a very important application in GAN. Means when a text is given, then you generate an image. Okay, this small bird has a pink breast and crown, and black primaries and secondaries. As you can see that with this input text, The generated image, on one side that the real thing is the text and the images are being generated. You give this text to the computer using this adversarial network, it will be able to generate the images. How beautiful they are. The white and yellow flower have thin white petals and a round yellow stamen. Can you see how beautifully they have been, generated? So these are all interesting. Then you can translate. There is a can of apples, and can you just convert it to a can of oranges? These are all like magic. Okay, one of the apples is very dark on the left side. You can see. Similarly, on the orange side also, at the same position, there is an orange which is not very. It's almost slightly maybe rotten or whatever it may be. It's more greenish. So every apple, it just takes the place of an orange. Every orange takes the place of an apple. So this is how using GAN you can paint. So as you can see that if you want the paint of sky, it's painting sky. If you want that to paint a dome, it's painting dome. And all you can enjoy the painting using this kind of things. So how beautiful is the whole thing. This is, AI living portraits. So you have seen that Mona Lisa's picture. Then the Mona Lisa's picture, how you can make it living. So here, as you can see, that using the same kind of adversarial network, the original input image is this Mona Lisa. You can make it a living portrait. So these are all, very, very interesting kind of things which neural networks can give you today. And thank you very much for attending. I was expecting that, okay, much more number of students will join. I do not know how many of you have joined, but then I thank you very much. I have taken much more time. So in detail, one will be taught in the classroom. Naturally, this is just to generate the curiosity amongst the students that how beautiful. I have not touched upon even many areas. There is no area today which is not being affected by this the learning systems. Every area. I have not touched about the intelligence, AI and learning systems in IoT. IoT we talked about last time. I have not touched with how AI can be used in the business processes. That's a very important area. I have not touched about how, of course, Professor Majumdar has given a very good example of AI in healthcare. But AI in healthcare again involves lots of other applications as well. Professor Majumdar has given a very elaborate explanation of that. So artificial intelligence is a basic backbone of today's life and in today's computing systems. Everywhere it will be used and is an integral part of data science. Anyway, thank you very much for your patient hearing. And okay, so I am now stopping the sharing of the screen. Yes, so
Thank you. Thanks a lot, sir, for this enriching presentation, enriching session on the foundations of machine learning. Thank you, sir, again. And I hope everybody is
students,
getting
just one or
engaged.
two comments do you have to give? Any question? So is it okay?
Sir, excuse me, sir.
Yes.
Hello, sir. Sir,
Yes,
I was
yes.
saying that, sir, can you please share this PPT, sir? Because it would be note important things which we can visit or see at our leisure time, or when we are just we want to visit it again. The PPT would be helpful, sir.
Yes, sir. If you can share the PPT, it will be helpful for us.
Yeah. Okay.
Lots of questions
And
we are
any
generating at this
question?
moment in our
Any
mind. But
question you can just share the questions with
Sir,
Professor
one question, sir. In one
Chandranath.
of these, Sir, one of the questions, sir, is there that in one of the slides, GAN was written, GAN. What is actually this thing, GAN? In
This
brief, you
is
can.
generative adversarial network. Okay,
Okay,
this
sir.
is one of the more recent neural networks. Okay, so so this is having a different type of, because it's all generative kind, because it was creating art, it was creating paints, it was creating from a single portrait, it was making it a sort of a I mean, living portrait of Mona Lisa. It can create the images from the spoken words, your speech to image generation. So all kinds of, it can generate the fake images to resemble it almost like an original image. Okay, so this is a very, very interesting concept on which a lot of work is being done. So you have to learn it, because everything, it's a what I have covered now, it will be a 2-year course on artificial intelligence only. And also in data science, this will be at least say 2 or 3 courses it will be covered. So that the whole area is very huge. In a nutshell, and very rapidly, I went through all the diverse domains. Still, I could not talk about everything. Okay. And all the best, because the next speaker is waiting. So thank you very much. So who is the next speaker?
Sir, Dr. Kausik Basak.
Okay. So Kausik is here.
Yes, sir. I'm
Yes,
over
sir,
here.
he's here.
Okay, yeah. Mr. Kausik Basak will be now. Okay.
Thank you, sir. Thank you for this session.
Okay. Thank you.
So,
Thank you, sir. It was really a nice session, and I hope participants who are attending your sessions could learn about the basics of the machine learning, as well as some concept about the neural network as well. So, Shaptarshi, can you see my screen right now?
Yeah.
yes, it's visible.
Okay. Okay, so good afternoon, all of you. With the basic concept that you have already got from Professor Ray's lecture, and some of the topics that has already been covered from yesterday by Professor Mujumdar as well. So today I'm going to say something about this decision tree and the random forest. Basically, I will talk about how a particular decision tree can be created using some of the algorithms, and how a random forest can be modeled based on the limitations of the decision trees. Okay. So now, before going into detail about this decision tree, let me just recollect few of the things that we already have learned from Professor Ray and Professor Mojumdar. So this is a kind of supervised learner in which we will be dealing with mostly the label data. Label data means associated to all the observations or feature values, we will have the class labels. That means the model will be trained based on some kind of label data set. So that's how the decision tree and random forest both falls into the part of the supervised learning mechanism. And the next thing that I just want to mention, like in neural network or Bayesian classification or this kind of machine learning algorithm, what we learned was there was some kind of mathematics that we need to develop, which will definitely try to understand the hidden pattern that resides in the data matrix. So that was those algorithms are kind of parametric techniques in which the whole model will be trained based on the different number of observations or based on the different number of training data set. So through which our goal is to parameterize the different equation or the equation parameters over there. But in case of decision tree, it is a kind of a non-parametric approach, first of all, because you will see there are some kind of measurement metrics we are going to use definitely, but there are no as such dedicated mathematical rule or model is present by which we can say, okay, these parameters we need to train based on the training data set. So that's why the decision tree is kind of a non-parametric approach. And eventually we'll get to know it is a very much intuitive and very simple to form. And in today's world, also in a lot of industries level, as well as in healthcare sectors, in lot of sections, like people are using decision tree and random forest based say pattern recognition or classification or decision making process. Okay, because the representation visualization is very much simplistic compared to the other machine learning algorithm that we have in this particular paradigm. Now moving forward into this decision tree first, let me just first tell you some of the terminologies that we are going to use over here. So our task will be in this decision tree model to create a tree-like structure based on the training data set, so that when the algorithm or the machines will encounter an unknown observation, then it can track all the tree path and it can finally gives the accurate classification or what kind of category of that particular observation it will be. So in this particular tree-based architecture of this decision tree, there are few things that we need to keep it in our mind and which will definitely eventually be used throughout the lecture. First one is the root node, because root node is from where we are starting the creation of this particular tree. So we need to find out based on some of the metric that we will be learning in this particular session. And this root node has a very vital point in this particular aspect, because given a particular data set or a feature matrix, this root node defines what is the dominant feature present in that particular problem. Okay, so moving forward, then we will be dealing with decision nodes as well. Over here, you see, this is a kind of tree structure that I have given, for example, like which considers three different categories of fruit bowls. One is apple, one other is cherry, and another one is the lemon. Now, if we'd like to categorize these three different kinds of food, so let us see, like first parameter that we are choosing, first feature that we are choosing is the diameter is greater than equals to 3 or not. So if I'm choosing this particular feature and try to separate out all the fruits that's present in this particular actual problem set, so it gives me two different buckets. In the false bucket, I am getting all the cherries over here. In the true bucket, I am getting a mixture of fruits. Now, if I am just looking in this false bucket, you see all the cherries has already been categorized. That means we do not need to do any kind of further classification over here, or we do not need to find out any further feature based on which we can do the further branching of the tree. But over here, there is a mixture of fruits are present. So that's why we need some another features definitely to do some further classification. So in the next stage, what we are choosing is the color is orange or not. So this is another feature that we are choosing from the feature matrix. So based on this particular feature, again, we are getting two different branches. One is giving me the red color and another one is giving me the orange colors. So this is the apple bucket. Now it has been formed, and this is the lemon bucket. It has been formed. So all these three nodes, you see, there are no mixture of the fruit. So that's why we do not need any kind of further branching, because they have already been reached to the final classification level. But in middle of this particular tree, in a particular level of the decision tree where we are getting a mixture of different fruits are present. So this type of nodes are known as the decision node, because decision node means that particular node requires further branching or the further splitting. Okay, and rest of the other nodes like this one, and this one are can be termed as the leaf node or the terminal node over here. So because they have already reached to the final classification level, and we do not need any kind of further splitting out all this particular node to do the final classification. So these are known as the leaf node or the terminal node. So these are some of the nomenclatures or terminologies that we will be using throughout this particular lecture, where you should remember that what is the root node means, what is the decision node means, and what are the terminal node means. Okay. Now next, moving forward, there are few metrics that we need to consider in this particular creation of this decision tree. Because if you just go back and look into this particular example, the human mind can easily figure out like whether the diameter is greater than equals to 3 or not. like for apple and for lemon, it will be definitely greater than equals to 3 because it is already been set into our human mind. But how to make it understand to a from a machine's point of view? Okay, so for that we need to have some sort of matrix by which we can find out like which feature should be taken at which point, and based on that how many number of branches we could form. So there are 3 different metrics at this particular stage that I am going to tell you. One is the entropy. Entropy means it's a measure of randomness. That means how randomly distributed the patterns are in a particular level or in a particular node. Over here, if you just see in this particular data set, here is a mixture of apple and lemon are present. So it's the distribution is quite random over here. So that's why the entropy of this particular node is quite high, where we do some based on some kind of feature selection. If we just do some decision split, in this particular stage, you see the randomness is quite low. So that's why the entropy at this particular child branches are kind of very low. So that is the goal of this particular entropy model. We have to go from higher entropy region to lower entropy region. So that is the goal while we are creating any kind of decision tree. That would be the goal of a kind of decision model based on which we can do the split. Now there is another more, and this is definitely the mathematical expression by which we can compute the entropy of a particular node at a particular stage of the decision tree model. So FL corresponds to the probability of a particular outcome. Okay. Now there is also one more parameter based on which we can do this kind of choice of the features, as well as it will lead us to the decision split, is the Gini index. Gini index is basically the measures of the probability that a particular variable being wrongly classified. Okay, so based on this feature also we can see, like in the similar way, if we just measure, so this is the expression of the Gini index that we could use to make any kind of, to find out which feature would be the best fit to do some kind of split at a particular level of the decision tree. So based on that, this particular value of the Gini index for the different features, we could select one feature at a time. Okay, so now this is the Gini index, and the third one is the information gain. Information gain is one another metric that we could use to choose which features could be used to do the decision split over here. And information is nothing but the difference between the entropy. So for example, if these are the 2 consecutive levels of the decision tree, then these should be in the higher entropy obviously, and this should be in the lower entropy region. So difference between these 2 entropy regions, that means E1 minus E2, is basically the information gain. So from here we could understand one thing, like if the more the information gain for a particular feature, that particular feature can be considered as the dominant feature in that particular level of for the decision split. And also, if I'm just considering the entropy value, the lesser the entropy value for which I am getting by utilizing some feature to do the split, so that particular feature can be considered as the dominant feature in that particular level of the decision tree, similar to the Gini index as well. So for entropy and Gini index, we will go for the lesser count, whereas for information gain, we will have to go for the higher count values. Okay. Now let us try to understand how graphically a particular decision tree model can be created and how does it particularly work. So now this is a problem data set that has been given to us. So this is a bowl of fruits are present in which apples are there, grapes are there, and the lemons are there. Now, when I'm saying the goal of this particular problem is we have to classify these different types of fruits that presents in the bowl. So now when I'm talking about we have to classify these different types of fruit, definitely from our human intellect, we can say like there are 3 different fruits are present. One is apple, one is lemon, and one is cherry. So now, grapes. So now But try to think very carefully when I'm just talking about, with okay, this is apple, this is lemon, and this is grapes. Basically, we are judging all these apples in our brain based on their colors, based on their shapes, their diameters. So all these are kind of features of this particular fruits that we are considering. So what we have to do next, we have to create a kind of feature database. So this is a feature matrix based on two different features we are getting. So we have computed color is one feature and the diameter is another feature. So just for a very easy thing, I'm just considering two features over here. There are a number of other features can be computed also from this particular problem set. And associated to that, we also have the class level. Because over here we are dealing with a supervised learning mechanism. So that's why this class level information should be there along with as a prior knowledge for that problem set. So now in this particular feature matrix, what I could get is if the red color is red, diameter is 3, it will be an apple. If the color is yellow, the diameter is 3, it would be a lemon. Or the color is purple and the diameter is 1, it will be a grapes. So these are the different kinds of feature or observation. So each row corresponds to an observation over here. So this is a feature vector, this is another feature vector, and this is the class level information. Mind it, this is not a feature vector. This is the class level information which we need to train our model, because we are dealing, so decision tree is a supervised learner over here. Now from these particular features are present, the next task will be how we could figure out the which features could be utilized to do the splitting based on the say information gain I'm considering over here to do the split over here. So we have to find out which features could be the dominant feature which I could take as the beginning to do the first split, or the which could be used as the creation of the root node from which we can get the two different types of branching. So from here, what I am devising, so these are the conditions, like whether the color is purple or not, whether the diameter is 3, if the color is yellow or not, if the color is red or not, and diameter equals to 1. So these are the 5 different conditions that I am deriving from this particular tree-based structure. Now, which conditions can gives me the best split at the beginning level by which the information gain will be high? So from here, what I could understand, if the diameter is 3, if I am choosing, so the number of counts of here, it's predominant compared to the other conditions. So let us just take diameter equals to 3 as the dominant feature over here and start creating the decision tree from the root node. So in the root node, definitely the feature that I am selecting is whether the diameter is greater than 3 or not. So this is the root node that I am creating. So based on this condition, either it could be false or it could be true. So if it is false, then all the grapes coming to a particular bucket, and if it is true, then all the other fruits are coming to another bucket. Now, if I am just closely look into this particular 2 different branched out buckets, what I can see that over here all the fruit types are same. So that's why like no further splitting is required for this particular node. It has already been reached to the leaf node. So this is the root node, this is the leaf node we have already been reached. Now let's move, if we just move to this particular node. So this node particularly requires further splitting because there is a mixture of different fruits are present. So to do that thing, we need to select one more feature based on which we can do this further splitting as well. So another feature that I'm selecting as the color equals to yellow or not. So again, if I'm just selecting this particular feature as the decision node, and subsequently I'm getting 2 different branches for it. One is the false branch, another is the true branch. So in the false count, I'm getting all the apples are over here. And in the true type, we are getting all the lemons are over here. So now we can say, like by using these 2 different features, we could categorize all the different types of fruits per 100%. That means all the fruits has been classified with 100% accuracy. Okay. So now this is how a particular decision tree can be created. Now let us just look into this particular term, like what are the different mechanisms are there by which in practice we definitely create this kind of decision tree. For example, like talking about different algorithms, like there are CART, which is a abbreviation of classification and regression tree. There are algorithms based on ID3 model. There are big algorithm based on C4.5 model. So like there are different different algorithms are present by which we can create a decision tree model. Okay, so and all these algorithms, they do use different sort of metrics to create the decision tree over here. Over here in this particular session, I'm going to discuss in detail about this CART model. So like this CART model, the full form of it is the classification and regression tree. So from the name, you can get an idea like this kind of tree-based structure can serve the purpose of both classification as well as regression task. So whether we are doing any kind of contiguous number prediction or whether we are doing any kind of classification for different class levels, this tree can be formed for both, can serve the purpose for both the cases. Okay, and as in for measurement metric, we are going to use the Gini index in this particular model of this decision tree. So let us take an example of it and let us go deep into this particular model and see how this particular algorithm, how the mathematics can be developed to create this particular decision tree using CART model. So over here, for an example, I'm considering a data which shows us like there are 4 different features are present, like outlook, temperature, humidity, and wind. So these are the different 4 weather conditions based on which there is a decision that whether there will be a tennis play or no play. Like based on these different 4 weather forecast, like the decisions could be made, like whether there will be a play on that particular day or whether there won't be any kind of play on that particular day. So these are the past 14 days data I already have at my exposure, and based on this past 14 days data, I need to create a decision tree model over here. So over here you see like the number of features that we are dealing with is 4: outlook, temperature, humidity, wind. So that means outlook is a feature vector over here. Temperature is another feature vector, humidity is another feature vector, and the wind is another feature vector. But decision is the class level that we are dealing with. Because as I said, like we are talking about supervised learning mechanism, so we need to have the class level information as a prior knowledge, because without it, this kind of supervised learner cannot be trained. Okay. So we are dealing with now 4 different feature and associated class level for the 14 days of data. Now, if I'm just going into this CART model and try to understand what we need to do, we have to find out the Gini index for these different features, first of all. And from there, we need to figure out which particular feature could be used as the root node first, because that is the from root node only the creation of the decision tree will begins. So that's what, like based on this Gini index measure, we have to find out what will be the dominant feature among these 4. Okay, so and subsequently when I'm utilizing, when I have found out some dominant feature from these 4 different feature set, so based on the feature label, so these are the feature label over here. So for outlook, if I'm considering, you can see there are 3 different feature labels as present: sunny, overcast, and rain. So for temperature, there are 2 different feature labels are present: hot and 3 different feature labels are present: hot, mild, and cool. For humidity, there are 2 different feature labels: high and normal. For wind, there is also 2 different feature labels. One is weak and strong. Why these feature labels I'm just pointing out specifically? Because when I have found out a particular feature as a dominant feature, whether it will be used for the root node or the decision node, the next from that root node, I need to create number of branches. So that branches will leads how many number of class labels are there over here. So as we are dealing with some kind of nominal data over here, so that's why like for Outlook, as there are three different features are feature labels are present. So these three different feature labels will pointing me to the branches, three different branches from that particular node. Okay. So now let us just start creating the decision tree based on these informations that we have. Over here, let me tell you, Gini index can be measured by 1 minus summation of probability square. So this is the equation that we are going to use from this particular to form this particular decision tree using the CART model. So now let us just focus on the Outlook feature first. So we have to find out the Gini index for these 4 different features separately. And from the 4 different values that I will get, I have to think about which Gini score is giving me the lowest value, because Gini score is basically pointing me to the probability of the wrong classification. So that's what, like the lower the Gini score value, the better that feature could be utilized as the dominant feature. So separately, we have to take all the features. Over here, I have 4 different features are present. So separately, I have to find out Gini score for this Outlook, separately for the Gini score for this temperature, Gini score for this humidity, and Gini score for this wind. Let us just take the Outlook feature first. So from this table, what I can derive is the 3 different feature labels are present for the Outlook: sunny, overcast, and rain. And based on these 3 different features, how many yes decisions I am getting for these 2. If it is Outlook is sunny, I am getting the yes decision 2 and getting no decision as 3. So total number of instances is 5. For Outlook equals to overcast, I am getting 4 decisions as yes. Decisions means I'm talking about this decision. How many count I am getting for no, how many counts I am getting for yes. Okay, so this you can easily do by your own also. So 4 times I am getting yes decision, 0 times I am getting no decision. If the Outlook equals to rain, irrespective of all the other features, I am getting 3 counts for the yes decision and 2 counts for the no decision. Now this is the small table that I have created to find out the Gini score for this Outlook. So now let us find out Gini score when the Outlook equals to sunny. So how we could find out? If I'm just remembering the equation, 1 minus summation of probability square. Okay. So over here, how for the sunny, how many classes are there? Yes and no. 2 different classes are there. So definitely it will be 1 minus 2 upon 5 whole square and 3 upon 5 whole square. That gives me 0.48. For the Gini index of the Outlook equals to overcast, similarly, I could find out how 1 minus 4 upon 4 whole square minus 0 upon 4 whole square. That will gives me 0. And for Gini or index of Outlook equals to rain, I will get 1 minus 3 upon 5 whole square minus 2 upon 5 whole square. That gives me 0.48 again. Now, what could be the total Gini score of the Outlook? So over here, I am utilizing some weightage for each of these individual Gini scores. And what is that weightage? Is the probability of occurrence of that particular feature label. So these are the feature labels that I am considering. So at the beginning, I'm finding out the Gini score for each of the features label associated to that particular feature. And then I'm multiplying it with the probability of that particular feature label. That means out of this 14 days data, 5 days there was Outlook was sunny. Again, out of the 14 days, 4 days the Outlook was overcast. And out of these 14 days, 5 days the Outlook was rain. So these are the probabilities that I could easily compute from the given feature table only. So if I'm just do this kind of simple math, so I'm getting the value as 0.342. So this is the Gini score for the Outlook. Now later, if we can do the similar way, Gini score for the temperature, what I am getting, it is leading me to 0.439. In the similar way, I'm just computing this table first. Like for the temperature, I have hot, cool, and mild, these 3 different levels. And associated to that, from the table, I'm getting the counts like 2 counts for yes, 2 counts for no, For cool temperature, 3 counts for yes, 1 counts for no. And for mild temperature, 4 counts for yes decision and 2 counts for no decision. So once I have completed the formulation of this table, then I could figure out in the similar way that I just did for the outlook. I'm getting the Gini score for the temperature is 0.439. Similar way, if I'm just doing the Gini score measure for the humidity and wind, I'm getting their Gini score as 0.367 and 0.428. So what I'm getting over here, all the 4 features I have and associated to that Gini scores I have already figured out. Now from this Gini score table, what I could get, the minimum Gini score corresponds to the outlook feature. So that's why this outlook feature will be taken, will be the dominant feature as a whole, and which could be utilized as the root node for the decision tree. So this is how the root node finding we can do based on this cart model. Okay. So now once this root node has been selected, so what will be the branches of this particular root node? Definitely we have to look for how many types of labels are there for the outlook. There are 3 levels: sunny, overcast, and rain. So definitely from the root node, there will be 3 different branches. So let us find out what each branch is contributing. So what we can see from the actual table that has already been supplied to us is if the outlook is overcast, then all the decisions are leading me to yes, irrespective of whatever the other features are present. So if the outlook is overcast, then definitely there will be a tennis play, irrespective of all the other feature levels. Okay, so that means for the overcast branch, we do not need any kind of further classification. We do not need to find out what will be the next decision node for this particular branch, because all the values corresponds to the yes decision. So it has already been reached to the leaf node or the terminal node for this particular overcast branch. But if we look into the other 2 branches, like the sunny branch and the rain branch of this outlook root node, then for the sunny branch, there is a mixture of decisions of yes and no. And from the rain branch also, there is a mixture of decisions of yes and no. So for these 2 branches, we need further classification based on some other feature. Now we are working in the level 2 of the decision tree. So level 1 was the root node from where we are getting the 3 different branches. One is sunny, another is overcast, another is rain. On the overcast branch, I am seeing that all the decisions leading me to the yes decision. So that's why we do not need any kind of further branch out of this particular at this particular branch region. So it has already been reached to the leaf node. But for the sunny and the rain, these 2 branches, we need to have other. There is a mixture of decisions that I am getting. So that's why we need to have another feature based on which further classifications can be made in this level 2 of this decision tree. So now I am operating in the level 2 of the decision tree, where we need to find out among these 3 features. Say I'm working in the sunny branch right now. So among these 3 features, which features could be the dominant one? And when I'm working in the rain branch, again for these 3 features, from this 3 feature set, which feature vector will be the dominant feature? Okay, so separately we have to compute these 2. So now we are no longer going to use the actual table. Instead of that, we'll be utilizing these small tables over here, because the outlook equals to sunny, this has already been given. So this is fixed. Now based on that, whatever the values I am getting from there, we have to compute the Gini score and the Gini index. We will be no longer working on the main or the actual table over here. Okay. So now let us figure out what could be the which features could be the dominant feature for the sunny outlook branch. So first I'm working with the temperature. So similar way I will compute this small table. For temperature, I am working with 3 different feature levels: hot, cool, and mild. So for this hot temperature, 0 count was for yes decision and 2 count was for no decision. For cool temperature, 1 count was for yes decision and 0 count was for no decision. And for mild temperature, one count was for yes decision and one count was for no decision. So let me just tell you one more time, this table I am creating not from the actual or original table, but from this particular table, because we are already working in the branch where outlook has been sunny. So we do not need any for other outlook equals to rain or outlook equals to overcast data. So based on these three table only, we need to figure out whether temperature or humidity or wind, which feature will be the dominant feature in this level 2 of the decision tree. Okay, so once this table has been computed or formed, then from there in the similar way, I could find out the Gini index of the outlook equals to sunny and temperature is 0.2. Similarly, for other features we have to do, like for humidity and for wind. So for humidity, like if I'm just computing the Gini index, so first of all, we have to figure out this table again from the table itself. And once the table has been formed, then from there we can easily figure out what will be the Gini score for the humidity when the outlook equals to sunny. So this is the prior condition that has already been applied. So Gini of outlook equals to sunny and humidity is giving me 0, and Gini of outlook equals to sunny and wind is giving me 0.466. So from this 3 Gini score, what I am getting is this humidity would be the dominant feature at this level 2 of the branch of the sunny outlook. Okay, so this is the next feature that could be utilized as the decision node in this particular level 2. Okay, so what could be this two output? Now if I'm just selecting this humidity as the decision node in the level 2 of the sunny outlook branch, then there will be two further further branches based on the feature level of the humidity. So one would be the high branch, another would be the normal branch. So that's what next we have to see, like when the outlook equals to sunny and humidity is high. So what I am getting, all the decisions are no. And when the outlook equals to sunny and the humidity is normal, all the decisions are giving me yes. That means like no further classification is necessary again. So this, if I am utilizing humidity as the decision node in the sunny outlook branch, then that particular decision node can leads me to the final leaf nodes where all the decisions has been separated or the class categorized. Okay, so this is the half of the tree that we have created. So this is the root node outlook that we have chosen. Based on the feature level of the outlook, there will be 3 different branches: sunny, or overcast, and rain. Now what we have got, like for the overcast, we do not need any further classification because it's already been reached to all the decision as yes. So this is the leaf node. So I have used different color codes over here to give you an idea about the root node, the decision node, and the leaf nodes. But for the sunny branch of this outlook root node, what I'm getting a mixture of decisions. So that's why I need to find out another dominant features in this level 2 of this decision tree. So this is the level 1 and this is the level 2. So in this level 2 of the decision tree, I found out that based on the Gini score, the humidity could be chosen as the decision node over here. And associated to this humidity, I am getting 2 different feature levels of it, high and normal. And what I observe, like if the humidity is high, all the decisions becomes no. And if the humidity is normal, so all the decisions become yes. Okay, so this part of the tree has already been computed. Now I'm remain with this particular branch rain. So over here we also have seen like this particular rain branch gives me a mixture of decisions. So that's why similar to this particular branch sunny, again we have to find out which particular feature could be utilized as the dominant feature by or which could be used as the decision node to do the further classification. Okay, so let us work on this particular aspect. So for now we are working on the rain outlook part. So again, for the rain outlook, we have to figure out the Gini score for the temperature, Gini score for the humidity, and Gini score for the wind. So first, the Gini score for the temperature I am getting, and it is coming out as 0.466. In the similar way, we need to formed this particular table, and we have to compute the Gini score of this particular temperature for the rain outlook. So I am getting it as the 0.466. If I'm just finding out the Gini score of the humidity and the wind, I'm again getting the Gini score of the humidity is 0.466 and Gini score of the wind is 0. So that's why like this, as this is a minimum Gini score that I'm getting from this particular stage of calculations. So the wind will be the next dominant feature which could be utilized in the rain outlook branch to do the further classification. Now, if I'm using wind as the decision node in this rain branch of the outlook, in the rain branch, then how many branches, further branches it could create? Definitely based on the different feature labels of it, like means weak and strong. So let us just see what would be the values when the wind will be weak and when the wind will be strong. So what I'm getting, if the outlook equals to rain and the wind equals to weak, then all the decisions giving me to the yes decision. And if the outlook equals to rain and the wind equals to strong, then all the decisions leading me to the no decision over here. Okay, so that's why like that means there is a full 100% categorization of all the decisions. There are no mixture of decisions that we will get. So that means we do not need any kind of further decisions, and all the leaf node has been reached to this particular wind node of the rainy outlook branch as well. So if I'm just finally draw the tree, it could be look like this. So this is the complete decision tree using the cart model for that particular problem set that I am working with. So first outlook will be the root node based on which sunny, overcast and rain are the branches of it. Overcast is leading me to the leaf node. Then for the sunny, we need to find out another decision node. Humidity will be that decision node, and the feature labels for this humidity feature, that means high and normal, are also leading me to the leaf node. Also on the other hand, for the rain branch, wind will be the decision node over here, and based on the feature labels of this wind, like the strong and weak, it will lead us to the leaf node formation again. So this way the final classification can be find out for the data. Now from here you could understand, like if this kind of tree-based structure can already been figured out from a given table or from a given training data set. Now once a unknown data set has been given, suppose for example I'm giving you like outlook equals to sunny or humidity equals to normal, temperature equals to hot, wind equals to strong. So now based on that you could easily figure out like which path I should traverse, and based on which what would be the decision associated to that particular unknown observation. So that means, so that is a very biggest advantage of this decision tree model. One thing is like it is definitely very much easy to formed, because over here you just see, you have seen like I'm utilizing the Gini score. That is a metric. That is not a mathematical rule by which we are training the model. That is a metric. So, and we are not parameterizing over here any equations or any mathematical description, because that's why it is a non-parametric technique. But in contrast to that, like if when we are working in the neural network or Bayesian classification or support vector machines, there we had dedicated mathematical rule present by which we have to do some sort of training the model, and during the training purpose we need to do the parameterization of those equations based on the training data set. So that's why those are kind of parametric techniques. But decision tree is a kind of non-parametric technique, because we are not parameterizing anything over here. We are just creating a decision tree-based structure based on the data set that has been supplied to me. And from there, we are trying to find out what could be the class or what could be the, say, category of an unknown observation over here. Okay, so that's why you could understand the training process will be relatively faster. That means computationally, the decision tree is somewhat faster to other algorithms, because the training process is very much easy over here. Based on a simple calculation of the Gini score, we could figure out what could be the structure of a particular decision tree from a problem perspective. Okay. Now that is one advantage. Another advantage is like it is very much easy to understand. Like for a particular problem, for example, say for this problem, so I am saying you this will be the decision node, this will be the decision tree for this particular problem set. Now if I am just giving you an unknown observation means I'm giving you all the feature values but not saying you what will be the class level. So you need to have figured out what would be the class level given all the feature values over here, or feature levels are there. You could easily say, like, given those kind of unknown observation, what could be its particular class. So human can easily means given this particular structure of the tree, you can easily perceive or you can easily visualize what could be the class of that particular unknown observation. But you cannot do this thing for the other algorithm, because those algorithms basically they are doing some kind of mathematical computations are happening. You don't know what is happening inside. The machines know and it is doing the process. But from a human perspective, if I'm supplying this particular decision tree and I'm saying that this decision tree I am formed for this particular problem set, so given an unknown feature, you can easily say from the just by seeing this particular type of decision tree what would be the class level of that unknown feature. Okay, so this is another advantage, and this is like a very big advantage in the industry level as well, by in which, like, while presenting a particular kind of machine learning model, people in front of you, in front of them, like whom you are presenting your work or your machine learning model, they could easily understand what would be the flow of the algorithm. Okay, so this is from the representation or visualization point of view, it has a very good advantage as well. Also, one more advantage is, like I said, like it is computationally, it is very much fast enough. Okay, so now compared to this is the CART model that I just talked about. Similar to that, we have ID3 model. Okay, so in the ID3 model, which is known as the iterative dichotomizer. So iteratively, it is dichotomizing between all the branching. We do all the branchings, and it is figuring out what will be the what will be the features that could be utilized as the dominant feature at a particular level of the decision tree. Now over here, the process of the algorithms will remain the same. Like at first, we need to find out that among the features, what could be the dominant features by which I could use as the root node. Then in the subsequent level of the decision tree, I again have to find out like which features could be utilized as the decision nodes. That's way, but only the measurement matrix is going to change. Earlier in the CART model, we use Gini index, but over here we'll be using information gain to create this particular ID3 model. Okay, I'm not going in detail about how we are doing this ID3 computations because we have serious limitation of the time. So similar to that, we have C4.5 model as well. Basically, C4.5 is a modified version of the ID3 model. So there are some kind of bottlenecks or limitations present in the ID3 model because it can only deal with the nominal values, and data set must not have any kind of missing value. So that's why, like the ID3, to overcome those kind of limitations, like Rose Quinlan, who was the inventor of this ID3 model, has redeveloped the particular model and named it as the C4.5. So what we are doing in the C4.5 model, similarly to the ID3 model, where we are measuring entropy and the gain ratio, entropy and the information gain. Here we are measuring one new part which is known as the gain ratio. So gain ratio is nothing but the gain, information gain, divided by the split info, and split info can be computed through this equation. So you could do work on this the same particular data set that I have used over here, and you will get like what is the decision tree that it is going to create. So these are the different algorithms that we are dealing with in the decision tree. Apart from that, we also have some Weka models, some other decision tree algorithms. But in this particular session, I'm just highlighting on this particular CART model only. Okay. So now let us look into the particular part, like which I already been told. Like there are some advantages of this particular decision tree, like the computational trying to train a particular model is less, and definitely like in case of Bayesian classification or any kind of other machine learning model, we do have to normalize or standardize the data first. So which we do not need to do over here. And lastly, it is very much intuitive and easy to comprehend and explain in the like scientific community as well. Definitely at the same time, this particular decision tree algorithm has a lot of disadvantages as well. What are those? Basically, it is a kind of unstable. That means you see, like whatever for the CART algorithm specifically, so all the Gini score that we have measured, so based on the counts. So if somehow one particular feature label is misinterpreted, so that means that counts will be altered. So corresponding to that, Gini scores will be altered. So that means any small change in the data will lead us to the big change in the whole decision tree model as well. So this is a very one of the disadvantage of the decision tree. Then when we are working with a very big data set where we are dealing with a lot of features that are present, and so they are like, it becomes sometimes complex compared to the other algorithm, and it can take more training time. But normally the training time of this decision tree is very much less. The third and the biggest disadvantage of the decision tree is it is prone to overfit. So this is the very biggest problem of the decision tree, like which comes from, like if the data set or the feature matrix that we are working with is too much of noisy, like Professor Ray just told you, like noise is inevitable in nature. You cannot eliminate this particular part. So every data that has been generated from a system, either from camera, either from any medical equipments or any kind of satellite images or any kind of communication data, everywhere you will find some kind of noises present. And it is inevitable. You cannot neglect or you cannot just abolish this particular part. So that's why, like if the data set is too much of noisy, then what happens? That the decision tree model tries to learn the noise parameter also. Over here in the machine learning, what we are actually doing, all this algorithm, they are learning the hidden parameter that are present in this particular different features. But if the feature data are too much of noisy, then the drawback of this decision tree is it tries to learn the noise as a feature only. That times it creating a lot of problem. So at that particular time, it will not gives you a proper classification accuracy, and it leads to the overfitting issues. So how to reduce this particular part? So instead of that, like these issues can be tackled into some computational domain, but this particular overfitting issues is a very big disadvantage of this decision tree, and we need to focus on this particular part. Okay. So now let us try to look into this particular thing, like how we could figure out this, how we could overcome this overfitting issue of the decision tree model. Okay. So now let us try to go in a little bit of math. Let us try to bring over here. So in this machine learning problem, basically what we are dealing with, we have a feature matrix and associated to that class levels, because we are working in the supervised learning mechanism. So we have a feature matrix associated to the class levels over here. So now what is our goal? We have to find out a function, or we have to fit a function depend on this feature matrix by which we can identify the class. So this is the goal. Yi equals to function of some function of fxi. This we have to model through the machine learning algorithm. But practically what we are doing, so practically we are doing yi equals to f hat of xi. So some approximation we are doing, plus some error will definitely be occur. Means never the time you will get 100% accuracy. Even if you are getting 100% accuracy, it will be considered as your algorithm is fault. It is not actually properly working. So that is the reason every time you won't find any paper by which you will get 100% accuracy for any kind of machine learning algorithm for any number of problem domain. So definitely there will be some kind of error for which there will be some amount of misclassification. What is this particularly error comes from? It is basically of two types. It would be the irreducible error, or one part is the reducible error. So irreducible error is due to the system or the inherent noise that we are dealing in the data set that we cannot do at this particular machine learning model. So to reduce the noise, either you have to work on the hardware part or the system calibration part. So all these things you have to do. But in the machine learning model, if we just want to reduce the noise, then we have to look into this bias and variance part. So this is the reducible error term that we need to focus on in this machine learning algorithmic part. What is this bias? Is basically, bias means how far are the predicted values from the actual values. So like for a given observation, you have its class level. Now your machine learning algorithm is telling you it has its different class level. So that means there is a deviation. So this is the bias, like how much deviation of the predicted values from the actual values. And variance means how scattered are the predicted values. That means for a similar type of observation, when you are getting multiple different like outcomes or the class levels information, so then it is showing as the variance part. So how scattered are the predicted values among themselves. So based on these two parameters, actually, if I'm just plotting two different things, so this is the low variance, this is the low bias, this is the high variance, this is the high bias. So you see this red mark, this bullseye region is basically pointing me to the actual values or the actual outcome. So when I'm having low bias and low variance, that means all the outcomes are pointed towards the center within this bullseye region. Now when I am having low bias but the variance is high, that means the spreading of the outcomes is too much of high. They are around this red region itself, definitely, but the spreading is too much, where they are concentrating to a particular point. Now, if the bias is high, that means they are shifting from the actual output and moving to other region where the intervariance is low among the outcomes. And high bias, high variance means entirely it is the decision is completely different. It is giving you some kind of haphazard outcomes. So based on these four categories, what we are dealing with, so high overfitting issue is basically coming from the high variance problem, and underfitting issue is basically coming from the high bias problem. So what we are getting over here in this particular perspective, from the particular perspective of the decision tree model, it suffers from the overfitting issue. That means it has a high variance problem in the output, so which we need to tackle over here. So let us just try to understand what is this overfitting and underfitting are actually meaning. So for example, this is the predictor and the output variable spread that I am giving over here. So this is the line. So this is the actual curve that we have to fit. So underfitting means what? The system that the model, machine learning model that you have developed is not actually understanding the hidden pattern of the data. So that's why it is giving you some kind of approximation, this kind of approximation where the error is too high. So this is the underfitting issue. Overfitting means what? So it is considering all the points as the separate one, and it is trying to formulate it as this kind of separated line it is formulating. So that means there are a lot of random noise are present by like for which the model itself is considering the noise as the data set also. So this is a kind of overfitting issue, and this is the optimum case where when the like bias is also low and the variance is also low. So then at that point of time, the machine learning model accurately can predict the hidden pattern of the data set. So this is the optimum case. So this is the underfitting case, this is the optimum case, and this is the overfitting case. Now how we could tackle this overfitting case, which is basically comes from the high variance problem in case of the decision tree. Let us just apply the same funda that in the long ago Britishers have used during 1947, divide and conquer. like the input data set will be partitioned into the several subsets. So like what I'm just trying to think, like if I'm having a lot of input data sets present over here and all the data are too much of noisy, so as the number of observations are becoming very high and all the observations are noisy over here, so if I can divide number of all those observations into different subsets, and then I try to create the decision tree for each of the subsets, then there will be less amount of chance that the tree will encounter the noises, because when I'm dealing with say 1,000 number of samples, so then the decision tree have to incorporate this 1,000 number of noisy data. Now when I'm creating 10 different subsets, each of consisting of 100 observation, for example, so for this 100 observation, definitely number of noises contribution will be low. So if I am just creating a decision tree on these 100 samples of the subset, then definitely I can say like that decision tree will be less prone to the noise. It will be somewhat immune to that noise. So similarly, for the 10 other subsets, separately we have to create the decision tree. That's how the whole noise or the whole variance part can be tackled. So the same thing that over here we are approaching, but what we are saying as the boot bagging model, or in full form we are saying it as the bootstrap aggregating. So there are two stages over here. One is the bootstrapping, another is the aggregation. So these are the two different steps that will be incorporated to overcome the overfitting issues of the decision tree. So what we are doing over here, so basically we are naming it as the bagging process. Okay, so how it could be developed, like if I'm having the whole number of subset over here, that will be this is a whole set I'm having, which is consisting of the original data. Now I'm dividing this original data into n number of subsets, and I am trying to create, for each subset, I'm trying to create a separate classifier model. And whatever the classifier model I'm created, so all the outputs of this classifier model will be taken as the ensemble classifier. So let me just clear you out over here. So this is the particular process of creating the bootstrap aggregation or the bagging process. Instead of creating a single decision tree on this original data set, now what I'm doing, I'm creating n number of decision trees for these small subsets. And that's way, those decision trees that has been created, I can see they are somewhat immune to the noise of that particular system, by which, like I can say, when they are giving me some kind of output, either we will do some kind of averaging or some kind of majority voting, based on which I could say like what would be the ultimate output of this ensemble of classifier. Okay. So in the bootstrapping, what I am doing, so bootstrapping is the process of taking how we are collecting the number of samples. So basically we are utilizing random sampling with replacement. That means if I have 3 different samples, for example, this is the original data I'm dealing with. So from here, I'm randomly taken. So these are the subsets that I have created. So from this original data. So how I have created? So I am taking the randomly different number of observations over here, although these observations are repeated. So this is known as the random sampling with replacement, like 313. So both these number 3 observations are repeating over here. Over here it is not repeating. Over here again it is repeating. So there is no as such rule present. So it is known as the random sampling with replacement. That means every time whatever the random subset we are making, in each of the subset there will be repetition of the observations or the repetition of the data might lie. So that's why these subsets could be created, which is known as the bootstrapping method. Okay. Now what we will do in the training process, so n number of training samples will be divided into 4 different sets. For example, I'm considering over here 4 sets are present. So over these 4 different sets or the subsets, you can say, I need to create separately the decision trees for each of these subsets. And once the model will be trained, that means once the decision tree will be created, in the testing phase, what I will do, the unknown data will be fed to all the decision trees And based on the observation or the features levels of this unknown data, each of the decision tree will generate some output. And when I am having a lot of other outputs present, so either I will do average or I will do voting. Now one question comes over here, while I will do average and when I'm do voting. So basically you see, as I said, so like this could be utilized for both classification and regression purpose. So if it is a classification task, definitely we should go for the voting. If it is a regression task, then we have to go for the averaging. Okay, so that's how this total training and the testing phase will consist of. Now this gives us an idea of how we are marching from decision tree to random forest. Because from here, from the name, you can get an idea like decision tree means what? It's a single tree. But random forest means what? It is a collection of trees. So that is the main fundamental part of the random forest, and why it is why it is becoming so much powerful in classification task. So basically what we are doing in the random forest is a like ensemble of decision tree, we can say. So given a particular problem sets like data, so what I will do, I will create n number of sets, and on this n number of sets I need to create n number of decision trees over here. Now once the unknown input will come, then this n number of tree will gives their corresponding output, and based on the application, like over here you see there are 2 apples, 1 banana, so this is a classification. So based on the application, either we will do majority voting or we will do averaging. So that's way like we will come to the final class. Okay, so this is the basic architecture of the random forest model. So there will be different trees, each tree will provide me different output. In the random forest, we will do some amount of majority voting. Like over here, you see 3 different trees, out of which we are getting 2 output as the apple and 1 output as the lemon. So 2 output will be, when it will be majority voted, this is final decisions created by this random forest model will be an apple. So this is how we can definitely overcome the issue of the overfitting thing in the random forest model, which was the basic limitation of the decision tree. And as well as it is becoming more powerful that even if the data set are too much of noisy, or if there is any kind of missing data present, this random forest model can easily deal with those kind of situation. Okay, so this is a particular application that I have just shown. So from the same figure, bowl of the fruits like earlier that we just took, if we just create 3 different trees over here, then for an unknown fruit, if I have to make a decision like which fruit it will be, so the corresponding observation levels are given to me, like diameter will be 3, grows in summer, yes, shape is circle. So this is the observations that has been supplied to me, but I don't know what will be the type of this particular fruit is. So what I have to do in this case, I have to put it for different trees separately. So tree 1 classifies it as orange, tree 2 classifies it as the cherries, and tree 3 classifies it as the orange again. So once I will get all the outputs, so I will do some amount of majority voting, and based on the majority voting, the random forest is giving me the final decision will be the unknown fruit is an orange. So this is how a particular random forest model is worked. So now, like coming down to the advantage, the final thing about this random forest model, definitely what we overcome is the overfitting issues that is happening terribly in the decision tree model. Definitely the accuracy is very much high because a lot of decision tree model separately it is working on that unknown data, and from the majority voting we are just bringing out the what will be the final class of the unknown observation. So that's why it's very much highly accurate, and it can estimate the missing value problem as well. So this is a definite thing that due to the limitation of time I cannot say at this particular point of time. But one thing just I want to clear that another one more advantages of this random forest is, like at the same time this particular model can be utilized for the feature classification task, as well as it can be used for the feature selection task as well. Like from this particular random forest model, if you just closely look, like at each stage, I am figuring out what could be the dominant feature. Okay, to start with the decision tree. The dominant feature means that particular feature is very, very much significant for that particular problem. So that's way, like the random forest or the decision tree model can give us some kind of feature ranking as well on the input data set. Okay, so these are the basic things about the decision tree and the random forest model, and it has a lot more applications, also industrial aspect. So what we did learn, like decision tree, first of all, it is a supervised learner, it is a non-parametric learner. Same time, it has its own advantage, the training time is very much fast. It could be the creation, the visualization, the interpretation is very much easy. We do not go to have to do some kind of standardization of the data set itself. But the biggest difficulties of the decision trees, it is over the overfitting issues, which is basically associated with the noise that are present in the data set, which can be dealt with the random forest model, in which what we are doing the bagging process. In this bagging, we are dividing the whole data set into n number of subsets, and each of the subsets for each of the subsets I am creating a separate decision tree. Now, once the unknown class observation will comes, once all the decision trees will be created. So once the unknown observation will come, it will be given to all the trees, and based on the levels of the unknown observation, based on the feature levels, each tree will gives me the output, and based on the majority voting, we can say what will be the final class for the random forest model. And what we have seen that through this random forest model, definitely the overfitting issues can be reduced. The algorithm will be more faster, even if I am utilizing a very big amount of data set, because I have already created a number of small subsets. So that's why the training time will be less compared to the decision tree model. So that's why like it will be more faster as well. So yeah, definitely this is all about the decision tree and random foresting that I just would like to discuss in this particular session. Thank you very much for your patience, and if you have any questions or if you want to know more about in this particular field, you can reach me to this particular email ID. Thank you very much. I hope I have not taken a lot of time, Shoptoshi.
Thank you, Dr. Basak, for your wonderful presentation. And I hope all the participants will be very interested in taking these studies further and exploring these topics further with all of us. And thank you once again for this wonderful presentation. And before our next presentation, I would like to have a short break of around 10 minutes. And so let us have a break, and we are meeting sharp at 4:40.
হ্যালো,
Yes, hello.
স্যার গৌরব বলছি। ঠিক
Yes.
স্যার গৌরব মন্ডল স্পিকিং স্যার। ওয়ার চন্দ্রনাথ স্যার কোথায় গেল?
There is actually a 10 minutes break. We have actually taken a 10 minutes break and we will resume from 4:40. Just 2 minutes to go.
Okay, good afternoon, everyone.
Yes,
So,
so this
is
our,
my
yes.
screen visible?
Yes, the screen is visible. Yes.
And just a minute. So, when I am changing tab, it is showing tab changing.
Yes, it is showing. Yes.
So, I think we may start from now. Right?
Sure.
So, dear students and participants, so very warm welcome. So, I know that it is not a time for conducting like workshops. Wonderful Sunday afternoon. But here also we used some majority voting scheme from the participants. Those requested us in the like in weekends because few participants are working professionals. So that's why we are organizing in this Sunday afternoon. Also, we are choosing Saturday, Sunday. And I hope you are enjoying the session from the past day. First, Professor Ajoy Kumar Day, then Professor Varun Kumar Majumdar, then Abhishek Ray, and Saptor Siddhas. And today also we have session with Professor Ekere, then Dr. Kausik and now myself Chandranath. We are all part of JIS ISR. It is JIS Institute of Advanced Studies and Research. So it is part of the JIS University, but we have currently three centers. One that is Center for Data Science. We are part of that center, and Dr. Kausik Basak is part of both like Center for Data Science and Center for Health Science and Technology. And we have another center that is Center for Interdisciplinary Science. And in my current session, the most challenging one to make you awake because some of you maybe feel sleepy. So please bear with me. So first of all, I want to start this session with some interaction. So I will ask you a few questions like what is machine learning? From the last day you are learning that what is machine learning. So any of from your side, what is machine learning? Please unmute yourself and answer. Or anyone from your side?
It's a method of thinking of machine
Yeah, but
by which a algorithm can learn everything.
yeah. So the learning is important, right? So we are imparting a machine some human like learning capabilities. As Professor Day and Dr. Vasak told, like in this today's era, everything is like learning. So machine learning has gone to almost every field. So even in the literature domain. So and there is some anyone can differentiate like in the perspective of machine learning. So one can write some program like addition or multiplication. So those are also written in C or Python like languages, and machine learning algorithms, those are also written like in some codes. So what is the difference? Both are codes. So in the perspective of the code, there should be some difference, right? So if I write some addition program, a plus C equal to a plus b, and I am writing some machine learning code, so both are programs, a few lines of code. So what is the difference? So anyone can give that answer in the perspective of coding? Because it is not like magical thing. So from the sky it will fall and it will learn. So we are writing some code from the computer science perspective.
Through the learning, actually we can improve our experience.
Yeah. So it's like human brain, right? So from a child brain, as Professor Day also told, if we consider one child brain, if we show him like this is digit 1, this is digit 2, this is digit 3. So inside their memory, some learning capabilities are going. But the addition program or multiplication, those are we are calling as rule based. Because some rule are associated there, some counting problem. So if I want to count, multiply 2 into 3, actually what we are doing? Like adding 2 plus 2 plus 2, like 3 times we are adding 2. So those are some sort of counting problem. But machine learning problems are, we are learning. So based on the experience, we are learning. So this is the basic difference. More details, if I get some time later on, then I will explain. So this is the basic difference. So addition, multiplication, these are also code, and machine learning algorithm, those are also code. But here, this will be some rule based. This will be some rule based. And here, machine learning code, it will learn from experience. So we will show the algorithm or the program or your model some images, as Kausik also shown you some fruits image. So apple, banana, lemon. So what you are learning. So based on the structure or the color. And in my session, I will go for some hands-on. So I will straightforward jump into some program. So but before that, we have learned few concepts of neural network from Professor Ajoy Kumar's lecture, and few concepts of convolution neural network. But the theory portion is huge. So as Professor Day also told, it may take like 1 year of course. But my objective here to make you understand like how the program is written. And for that task, I will choose like some medical images. Suppose one person's CT scans is provided to you. So or some radiologist. So he or she want to diagnose like whether that CT scan image is COVID affected patient or not. So the problem is you are given an image, say CT scan image, and your task is whether the CT scan image is of COVID patient or non-COVID patient. So this will be your task. So we will implement this model. And before going into that, few more examples. Here this task is called cat versus dog classification. Or here is also classification means we are learning in a supervised way. That means few images are there. Suppose one child is shown some cat picture and some dog pictures in the training phase. And in the testing phase or during the exam say, he or she has shown some dog picture, then he or she will be asked, oh, tell me what is this? It is cat or dog. So when there is two class, we are called this binary classification. And when there are multiple class, suppose here some cat images are there, some dogs are there, and few chickens are there. So there are multiple, more than 2 classes. So we are calling this as multi-class classification. Multi-class classification. Now, there are some other problems. When you are given one picture, you have to say whether it is cat or not. So the problem is whether it is cat or not. So this is also binary classification because one class is cat and another is others. So in our that COVID CT scan classification task as well, so you are given one X-ray image, so you have to tell like whether it is COVID patient CT scan or not. So that's why we are calling it as a binary classification. So am I clear to everyone what is the problem statement? If any doubt from anyone, then ask now only, because you need to understand the problem statement at least. So now that means we will be having one training phase and another will be testing phase. Training phase is just think in this way, you have exam, so before exam you are learning something or you are reading something, you are experiencing something. So that is your training phase. Testing phase is in your exam, like some problem has come, you have to perform there, right? So here also for in the training set, so there should be some COVID data, COVID patient CT scan, and also there should be some non-COVID CT scan. So otherwise you can't learn, right? There should be some samples from both the classes. So this problem will be with the perspective of computer vision. So you are providing some image or CT scan image. And in that testing phase as well, you will be given some COVID data and also non-COVID data. Because you will be in the exam, say you are someone has asked you like, okay, this is COVID patient CT scan or not. So although in this class we will perform the task on the CT scan, but our model should be generalized enough when it is trained on some X-ray data, it can perform pretty well in that cases as well. So when we are training with X-ray and when we are testing with X-ray, so it will also perform, it should perform quite well. So in machine learning algorithm, this is the main concept. Your model should be too much generalized, like our human brain. If I am trained with apple and orange, okay, my brain can also can be trained with some other foods like banana and cucumber as well. So machine learning model is like our human brain. It is too much generalized. It can learn multiple problems, or it can be trained with some experience. So what is machine learning in the Wikipedia page? Without wasting time, like I am moving toward the coding. So you can learn from this Wikipedia page as well. And this citation one, that is from Michel, it is one famous book. So you can consult by yourself. This domain is also like that, like machine learning. More you will learn, you will understand. And one disclaimer is that like those people have some problem to show some have some problem after seeing the radiology image, those can like leave this session, otherwise like it will be problem. Because I will show some CT scan image. Okay. So I am now showing some CT scan images. So here few CT scan images are there, so we have to understand or we have to learn whether this is from COVID patient or non-COVID patient or normal patient. So these are one image, another one, this type of images. And like one more thing, like why should I like take this type of problem? So there is like, if there should be some use. Otherwise, some problem is coming. So there is one way out that I am enjoying to solve some problem. That is one. And second one is I want to learn new things. So that is another thing. But there is also some financial criteria should be there, because from the corporate industry or some research, so funding is very much necessary. So those problems will stand in this current world, having the really impact on the society, one thing, and having the funding. So here one competition is going on, AI, that is artificial intelligence, against COVID-19, screening X-ray images. Those X-ray images are high quality. So for this class or for this workshop, I have chosen the CT scan image, but you can also take these X-ray images for training, and you can use the same model for your own task. And after the class, if you email me, I will share the model with you. So this competition is going on, and here is the deadline. Deadline is 15th July. And there is some prize money, I think. Yeah, prize money is 1,000 Canadian, and around 1,000 Canadian dollar. So you can participate here as well if your model performs quite well. So, but today's class on the perspective of the learning, and this is our objective, because in the AI community or data science community, those are trying to learn these models to fight against COVID-19 in their own way. So before that, I will use this ID. So there is one famous online ID, that is Google Colab. So you can perform with me. So you can search with Google Colab. There, then you just click here. Welcome to Google Colab. Of course, am I visible to my screen is visible and my voice is audible to everyone, right?
Yes, sir.
Yes,
As well as
yes, it's completely visible. Yeah.
Yeah. Sometimes actually like mute from your side, so sometimes I can't understand. So when you go into this link, there you can open new notebook. So I am not promoting the company Google, but still you can use it, like it's free. So new notebook, you just click here. So you should have one Google account. Obviously, you are understanding this. Yeah. So this is my Google account. I have logged in via this, and what I have done, I have uploaded the data in Google Drive, because I need to deposit some. So Google Drive, I thought it's a good place to show you online. So I just deposited there. I will show that one. For that, I need to mount that drive to this ID. So there is very simple like few lines of code. It's like the best thing of Python is it's like English-like language. So from Google Colab, from Google, and I don't have to like make you understand this, because it is English-like things you can easily understand. From Google Colab, import drive means we are importing drive from Google Colab. That's it. And we are mounting that drive.mount, where you have to understand like where is your drive is. So here, if you click here, so some files will come. So here you need to write content/drive. So then you can click here to run this cell, or simply shift enter at a time. Press shift enter. It will run. Okay, I'm getting some error. Yeah, it is in home, so there should be one font size. So now some link has come, so it is asking for authorization. So I'm going here, I will give some access to my drive. allow. Then I need to copy this code and simply I will paste it. Yeah, so it has been mounted. So now you just refresh these things. Here one button, middle button, it's showing refresh. So yeah, now your drive has come. So everything in my Google Drive, it is here. So here in Google Colab Notebooks, I have this data. In CT cough or CT scan cough, I have crane data and test data. In crane, I have this like COVID data, and in non-COVID, I have non-COVID data. Similarly, in test as well, COVID and non-COVID. In this folder, individual folder, I have few images. So you can see I have this .png images. Then I need to import I need to import few libraries because I will use some inbuilt functionality of one framework, that is TensorFlow and Keras, the libraries. I will use those. For that reason, I need to import. So you can remember this, or by experience you will understand. And in this ID, it will show yourself whether there is any syntax error. I will simply import few things. Import TensorFlow, SPF. I will use these things actually. Not that. So this tab you can copy paste from here or somewhere. I'll provide this on this, but later on from experience you can now. I plot for plotting if I require some plotting. I will put some. And there is another framework I use from PIL. Use flow. Here, insert flow. Exit this. Flow. Processing. From. So you need to provide the training path, where is your training folder is required, and test path you need to provide. So train path, I need to provide this one, and as well as I need to provide the test path. All the data is here. So train path will be this one. So here is 3 dot is here. So I will just right click and copy path. So train path I will paste here. And the test path also I will 15. So in machine learning domain, the more data you have, your learning will be that much better. Because it's like before exam, more, it's not always, but in most of the case, more you learn, more you understand, or more you have the experience. So lots of data is required. But suppose we have only 200 data and we need to augment the data. So there is few lines of code using what we can augment our data. More data we can generate, like we're horizontally flipping or shearing or some cropping. This I am just calling that function. By itself, it will generate few augmented data. This train data gen. Now I will use this image data generator. I will scale it in the grayscale, and I'll use a shearing transformation. So here I need to provide shear range, then I need to provide zoom range. There are other options as well. So if I like CT scan, it's like our human body is symmetric. So we can horizontally flip. So horizontal. Here you can see multiple options are coming. So I will use the only horizontal flip, not vertical flip. Now for the testing data as well, I will augment. So I am just copying this thing. And for the test data, I can also do this, or I can delete this one. As per my own choice, I can use, I can delete these things or not. It's my own choice. So for the test data, I am just keeping as it is. For the training data, I am augmenting. For the test data, I am not augmenting. Now, I need to count how many data I have. Training set is, this training data, it should come from here. This, whatever I have generated, it should come from here. So here I do these things. Train data gen dot show from directory, and I will provide this train path. This train path, and I will use 224 into 224 size image. So this size I need to fix. The target size will be 224 cross 224. Here the syntax I need to use comma. And as a whole, I can't pass all the data. So slowly, just like before the exam, you can read all the book at one time. So first day you read 16 pages, then second day you read 16 pages. So slowly you will learn. So here also it is calling batch size. It means at a time 16 data we are learning. From 16 data we are passing. So 16 data, then again 16 data, this. Another term is class mode. I need to define here. Consider this as syntax. Because in details, you can show short span of time. So it is showing found for 27 images belonging to two classes. Obviously, in the training, I have these two class, COV and non-COV. Overall, I have 427 images. So I will share the data as well. if you open, you will count yourself, it will show. Okay, overall it is. So what I will do now, I will do the same thing for the test data. Test data. There also test plot. So here in the test data we have like 256 images. And in the supervised learning, we should have some label. So like what Kausik told, like you have one bucket of or one basket of fruit. So this is apple, this is banana. So there are some label. So here also those images having label, it is COVID, it is non-COVID. So here these two, the COV and non-COV, this is our label. This folder name is actually our label. So here you can see these things. Let's set what class indices. It is showing COV and non-COV. COV means here it is 0 and it is 1. So non-COV means 0. Like in the cat or versus dog classification. Cat means 0th class, dog means 1. Here also the same. 0th class 1. Here now what we will do, we will sort all the data and label all the data. So there is one line of code, labels, sorted, training set, whatever we have given name here. Training set. Class indices, items. There is one syntax that is lambda. And the pair I print all the data set level. Of is now 0th class and non-COV is 1th class. And one more we can do, we can omit this 0 and 1. So for that reason, and we can make this capital C and this N as capital N. So it's just uppercase. Here, like this small line, numpy.array. So these details, those have knowledge of Python, they can easily understand. Otherwise, like if I get later opportunity, I can. Dot title is making up okay. So now it's coming capital C and capital N and those 0, 1s. Now the main model will use for here we will use the convolution and neural network. So that theoretical part is huge, but we are using the framework. So for the framework, because we are using the framework, so it is just 3-4 lines of code. So before going into that, I will draw one picture. So in neural network, what it is there, or straightforward, I will go to convolution neural network. It is called as CNN. Input, you have CT scan image. I am writing only CT. CT scan. So there is multiple layers in neural network, and perhaps you have heard the name of deep neural network or deep architecture. Deep means there are multiple layers, so it's going deeper. And in convolution neural network, there is one operation is conv at first, convolution. Then there is an operation named pool, or there is various type of pooling. Here we will use max pooling. So I am not going into the theoretical part in detail. So again, some convolution layer, again some pooling layer. In this way it is going, and at last there will be two nodes because we are working here for binary classification. So one node is
Dr. Adak, just sorry to interrupt you. Two participants have raised their hands. I think they have, Raj Bibot has raised his hand. Okay, so I think he has some questions.
Raj Bibot,
Sir, whatever the code you have written in the first, in the beginning, it is a combination of the TensorFlow and Python.
we are using the TensorFlow framework. Whatever I am writing in Python.
Achha. That means when you are importing the class that is tensor, that is that function is written over there.
Mm-hmm. Yeah. This is non-conv. So whatever I am writing, it is visible to everyone. Dr. Shri, it is visible. I am drawing one diagram.
Yes, it is visible. Yes.
Okay. So this is because we are working here for binary classification. If there is some classification, dog, cat, chicken, there will be 3 nodes. And there, if there is in the today's world, there are 1,000 class classification is also there, because 1,000 types of objects are in the real world. Like, for example, there are thousands of objects. Here, before that, here will be one. Again, I am writing once, or say softmax layer, but I am not going into detail of the mathematical foundation of this thing. But think in this way, at first we have convolution layer, then some pooling layer, then again some convolution pooling, and at last softmax layer, then conv and non-conv. So that means here we will generate 2 values. So here you are generating in this node, say 0.6565, and here you are generating, say 0.35. Overall, this summation should be 1. So which one is greater? This one? This one is greater, this value. So this image will be marked as COVID. Otherwise, if it was bigger, then it was marked as non. So we'll perform this in the model. Here, what I will do from TensorFlow, TensorFlow.keras import layers. Now I will create the model. And those layers were like formed in sequence here. Here, write sequential. Here, this S is in capital. Now, layers dot for convolution there is operation capital CONV 2D. And there is some numerical value because here we need to define the number of filters, number of what is the kernel size. Those are hyperparameters, but I am not going to that details as well. At first, my objective is to show you these things are not like that much hard when you are writing program using some framework. But inside the theoretical things is huge. But you can like write few lines of code to make the model. Value is on activation function. I believe Professor Day told that this say because it is we are using quant 3D. So here I need to pass 224, 3. There are other things also I can write, but for simplicity I am not writing those things. Some padding is also there. Well, let's write. Two types of padding is there. One is same and another one is value. And by default, if I don't write anything, so by default padding will be value. Here layers for max pooling to be that the kernel size is 2 cross 2. Then this thing I need to copy. There are multiple convolution layer, max pooling layer, so I am just so let's make 3 convolution layer, 3 max pooling. So here at first 16, then say I make this as 32, then this one I make as 64, between, and these other things are, and now I'm just deleting this input set. It will sequentially, it will obviously take the previous one. And here we may use the valid path. And by default it is valid, so I'm not writing it. So by default it will be valid. So in this way you can write. And now at last you need to flatten out. So flatten out all the images thing, all the previous layered nodes. You need to add one flatten pass. Then I'll add one here, suppose here there are say 128 number of neurons. So I am writing that one. Densely. Hence 128 and activation also introduce. I'm using J. And layers dot hence, and here we have number of class. How many number of class? We have 2 classes. So I have written 2 and activation. At last I will use softmax. I will use. So instead of this two, you can write, this model should be quite generic. So you can write in this way, training set dot number of classes. So it will automatically check how many classes are there. So it is two. So this, I have not made any syntactical error. Our model is on error. Spelling mistake, I think it is input. Now our module is completely ready. Now what we can do, we can check the summary of our model. So using this, we just check the model summary. So you can check the model summary overall at first convolution layer max pool, then convolution max pool, then pattern, then one fully connected layer or dense layer. After that also one densely connected layer where we have two classes. That's why here total trainable parameters or learning parameters, that is this much parameters in 55 lakh parameters. This much parameter, huge one. So we are thankful to Google. They are giving us this platform and I can draw a good picture of this model. So in some paper, perhaps you have seen some like pictures. So those are not actually drawn by hand. There are also some code. But model, model 1.25. I'm refreshing. So my model will save here in this place. File. Say we just give say model block dot say unit. So separate sources. So you can see one beautiful diagram has grown. You just refresh here on the left hand side. You can see you can download this thing as well. So you can in the research paper you can put this thing. So you can see here at first here the input output size, then convolution, max pooling, whatever I was drawing like hand drawing. So in the last layer there is it is two. That means I have two classes. So now I need to compile my model. Compile. Optimizer. One optimizer I should there because here the objective is to optimize the cost function. Optimizer equal to I use this Adam optimization function. So there are like quite a few theory besides this function. So you just call this loss is I use here categorical cross entropy or I can use also okay, and metrics just in the last lecture, like where Dr. Basak told, like metrics, like he was for decision tree classifier, he was using some entropy metrics, Gini measure, those things. Here metrics we are using the performance measure. We use here accuracy. Yes. Our model has been compiled. Here I am just writing the batch size because at a time I will pass 16 images at a time, not more than that. And there are few concepts of steps per epoch and validation steps per epoch. So there should be two phases, like one is like training and another one is testing. Here we are using the testing data we'll use for validation. So validation means like validity checking, whether our model is too much generalized enough on the validation data or some data. And here the whatever the name it is the test folder, actually those folder we are using for validation. It's pretty just some value model dot fit. So here I need to pass our training data, that is training set. And epochs means, here first write is epochs. Epochs means how, like think in this way, like before the exam you have read the book, entire book 2 times. Or like more you learn, more you understand, or more the good you will perform. That's the common concept. So if you learn the entire book say 100 times, so obviously you will perform well. So next for now, because there is shortage of time, we will run this program for 2 epochs. But theoretically, like you can use more epoch, like 100, or some algorithms you can even have to learn for like thousands of epochs. So next for this time being, we just keep it just 2. And verbose is nothing but some showing the outputs design. The main thing is steps are epoch and steps per epoch, and I need to pass the validation data as well. And validation step. You can see here it is giving me some like hint. Validation. If you forget this syntax, it will show you validation steps. So here it is, validation steps. So I am just writing that one. So if you forget whether it is step or steps, it will show you steps. So I am coming to this what it would be. So validation data, just for this time being, I am using the test set. Actual testing should come from the real world. Say if one patient is giving you the data to check your model whether it is COVID or non-COVID. So it should come from the real world. So here steps per epoch, say I am writing SPE, and validation, say I am giving the variable and say VS. So here I need to calculate. SPE equal to number of training set samples, samples divided by this, divided by double slash means it will give some integer divided by this batch size. VS, this validation step, it is test sample set samples. I could write this thing here, but unnecessarily for multiple epochs it will calculate. So it's better just calculate like before this one. All set. Now let's do. Our model is running. So see at the first epoch or first batch, this 26 actually, like we had how many training data we had for 27. So for 27 divided by 16, just calculate by yourself. For 27 divided by 16, yeah, it is 26.68. So if we use here single division, single slash, then it will give us this result 26.68 because we are using double slash, so the output will be SPE will be 26. So that's why it is showing the 26. So let's wait for a few seconds. So it's based on your like system, it will take time. So if I like give it here 20, epoch 20 or 100, so it may take like hours. So of the shortage of time, I am just simply using epoch equal to 2. Just wait. So here you can see its loss is accuracy is giving say 62%, 0.62 means around 62%. It is training accuracy. From the validation accuracy. And here Google Colab is giving you freely so what I have done, like because yeah, now the validation accuracy is very less. It is 35%. Training accuracy, though it is 62%, validation accuracy is 35.9%. So you should learn like more epoch, around say 20 or 100 epoch. Which is also hyper parameter. So you need to tune what will be your epoch value. Overall, it has after 2 epoch, this has come 40% validation accuracy. Now I will check from the real data. I will check. So here I have just searched on internet CT scan COVID. So I have got this to link. So this image, you just download it. I'm just downloading this. Save images. Say download. I have downloaded it. Now what I will do, I will simply upload here. There one button is here, upload. Just upload this thing. So now my image has been uploaded. So here I need to evaluate how my model is performing on the real life data. So here raw equal to image. So from field I have imported this thing image. Open. Then I will provide this path. Copy path. This thing. And here I will convert. I will simply divide and put it in on NumPy array. And I will resize it into, because our model is taking the input size 224 plus 220. Size it. Then I will divide this 255. So now you can see that picture here as well, or I will show you. So here, what I will do, and now I will predict the model, predict what the image is. This image is COVID or not. So that is traits equal to one variable. Model dot predict. Here, I will put one expanded version of that array. Expand teams. Then the row, and axis. So 0 in row. And so now it has been predicted. So I need to check what are the values of these traits. To see these plates, actually first one is 0.66 and second one is, or better just change this. So in the output we had two nodes. So first one this 0.66, 0.33. Second one is 0.33. So then we need to take the maximum, which one is the maximum and that level. So here simply we'll use the argmax of these plates into that. What argmax plate means, it is taking the 0th level. So you can print in a good way. So you just plot that image into that I am sure. Plot this thing, and under that image you can plot its level value. For here, instead of this 0, if we write here data set export labels, this thing, then it will show you it is COVID, Prof or COVID. So just simply you can copy this thing, put it here. It will show you the image as well as the class level. So here it is showing the image, and here is COV means it is COVID. So our model is predicted this CT scan image as COVID. And similarly, you can another image. So you can use this image to check whether this is working fine or not. For this, you can simply give this link as well. So what you can do and perform it in this way of WK, then put this link here, then minus capital O, then test.say. You are getting this image as test.jpg. Then I will simply copy this course. See. So instead of this image, what I will do, and here you can see that test image should come. So you just refresh this thing. So yeah, you can see here test.jpg has come. So what you will do, you will just give this path. So from the online link, that's here. So it also showing as this image is of a COVID patient. COV, the label is showing as COVID. But the thing is, you have only run for 2 epochs, so the result may be that much good. What you need to do, you need to just increase this number of epochs. So for that reason, I have already performed this task like before like few hours. So I have run the same program for the sake of time. What I have did, I have just put only the difference is epoch, I put 20. So for 20, here you can see my validation accuracy is around 66%. But whatever now in the class I have performed, its validation accuracy is around 40%. So more epoch you should. So here I have performed the same operation. This is actually predicting as COVID. And this actually it was non-COVID. So this is showing as non-COVID. So this model, because I have trained, I have learned my model few more epochs. So it gave me the correct result. That is actually this is non-COVID. Just like your experience. So if you read a book say 2 times or 20 times, so obviously if you have read like quite in a good way 20 times, so obviously your experience will be better. So same. So it is giving me non-cough. But in the class, whatever I have performed, it is showing me as a cough. It is giving me like not the correct result because I have done like lesser number of epochs. So that's it for now. So you can go through this link and check by yourself. Like there are some data sets is given, some data is given. You can download from here Kaggle website. Checks takes it. So using this same model, you just instead of the CT scan, you just put this type of images. Then just copying that one here. So just copy these things, this link, and check it by yourself. So your homework may be instead of the CT scan image, you just use this, use the chest X-ray images. So and if you want this code, I can simply share. Let's type it. If you want the code, just email me. As I said, that's it. Any question from anyone? Dr. Suman is here. Suman, our Suman.
Let me just check. I think he's not.
I don't. Yeah. So one small announcement is there that we may conduct the next session based on the curiosity of the participants. So this was the part 1 of this workshop session. So maybe end of the next month. So if we get some interest from the candidates, then obviously we conduct next on our session, and next session may be on big data and cybersecurity. And anyone from your side, any question related to entire workshop or anything? And we also intend to provide the e-certificates. Few days later, we will We're planning for that. Any question or any discussion you want?
Yes, so we are open for any kind of discussions and questions if you would like to ask regarding the whole workshop for the last 2 days. You can ask any questions or any queries you have.
Yeah, and one more thing, like in our institute, we are organizing these events like throughout the year, and you can keep your eyes on our official Facebook page, and we have also one YouTube page. Just search in YouTube JISIASR, you will get those channel, and these workshop videos will be available there. Our past workshop or webinars videos are also there, so you can check those as well.
And another thing that I need to mention is that anybody of you can reach to us at any time in our email IDs, or you can reach to anybody of us regarding any questions and clarifications or for further knowledge or something about these topics.
And just pasting our YouTube link. Yeah. Yesterday's workshop videos are also there, so you can check those as well. And you can share with your friends as well, those that have missed this opportunity. And this is our Facebook page. So if new webinars or new workshop is going on, you will get the notification from here as well. Also, in our institute website, you can also have the information what we are doing, our current research, what we are teaching. Currently, from Center for Data Science, we are offering 2 courses. One is for 2 years MTech in computer science with specialization in data science, and another one is 3-year MTech that is for working professional. And recently, we are planning to launch another diploma course, that is advanced diploma in information security. So you just, if you are interested, then you can have a look on our website or Facebook. Thank you everyone for your interest.
And thank you, Professor Adak, for this wonderful presentation.
The pleasure is mine.
Thank you. So if there are not any more questions from anybody, so we can conclude this workshop, and we will definitely be organizing such workshops in the future, and we will expect your wholehearted participation and looking forward to those.
Thank you very much. So, Prof, you may stop the recording at first, then we can
Yes, sure.